Good afternoon. You're welcome to today's class EMT1 or 2. We'll be looking at electromagnetic field theory. That is what we'll be looking at today in this class. So we'll be looking at electromagnetic field theory. And among the things we'll be looking at here, we're going to be knowing what vector is. What is a vector? Then algebra of vectors, the scalar product, which I know some of us did in secondary school, but today we have to move further and add some things to it. When we say a scalars are quantities that are simply defined by a magnitude. Scalars are quantities that are simply defined by magnitude. There are some people who say scalar quantities are magnitude. For whatever you want to say, scalars are quantities that are simply defined by magnitude. Now, for example, the mass of an object just has magnitude, so it is a scalar quantity. The mass of an object just has what's it called, a magnitude, so we'll call it a scalar quantity. Why? Because it has only magnitude. That is the mass of an object. The mass of an object, that is the mass of an object. So without scalar quantity, we wouldn't be able to model temperature or mass of an object. Without scalar quantities, we will not be able to do much in life or in science. We will not be able to do much in science. So that is to tell you that scalar quantity is important. It's important. Scalar quantities are important. Now, what is a vector? If I might ask, yes, most of us know what vector is from our secondary school. A vector quantity has both direction and magnitude, that is size. A vector quantity has both direction and magnitude. For example, velocity is a speed in some given direction. Let's say, for example, the wind. Velocity is a speed in some given direction. For example, the wind. And the wind is blowing at 8 meters per hour in a westerly direction. So these are examples of vector quantity. Vector quantity has direction and magnitude. Without vector quantity, we would not be able, or we wouldn't be able to model the forces acting on an aircraft. Now, if you look at the screen, the aircraft there, you see that there is force acting upwards, there's force acting downwards, which is the weight or the gravity, there's force acting towards the left, which is the drag there, and there's force acting towards the right, which is the thrust. So these are possible. Why? Because of vector quantity. Because of vector quantity, we can, or we could measure, we could model the forces acting on an aircraft. Now, we could also model the torque and circular motion. We could also model the torque and circular motion. So that is that. Now let's look at, just look at the screen. Which one here that you're seeing on my screen, can you identify the one that is a scalar or a vector quantity from what we've defined earlier on? Can you identify what, okay, this is, tell me if this is a scalar quantity or a vector quantity. So I just want us to go to that. Let me just give you 1 minute to just refresh your memory. Is velocity a vector quantity or a scalar quantity? Now, is temperature a vector quantity or a scalar quantity? Is mass a vector quantity or a scalar quantity? Is torque a vector quantity or a scalar quantity? What of momentum? Is it a vector quantity or scalar quantity? Speed, time, displacement, force, bank balances. What will you classify them? Will you classify them as vector quantities or scalar quantities? I leave that for you to answer. Now, by the end, what we'll be looking at now, by the end of this section, we'll be able to define what is meant by vector and differentiate between a vector and scalar quantity. That is one of the essence of what we're doing. Then algebraically manipulate a vector, then calculate angles between two vectors using scalar products. So we're just beginning this class. This is a word of introduction, but we still have to dive in because we have lots of things to cover. So wherever we can get to, God helping us, we'll see. So we will see wherever we can get to. Let's start with properties of vectors. Now, if we want to represent vectors, representation of vectors,
Really hold on, your lecturer will join you soon. Please be patient. Please be patient. Very soon. He's having issue with network, so please be patient.
We can represent vectors in many ways. I said we can represent vectors in many ways, and some of the ways in which we can represent vectors: one, if we have line joining the 2 points A and B, that is having a joining point A and B, we can use that to represent a vector point A to B using a straight line to join them. We can use that to represent a vector. We can write the vector taking us from A to B via AB, or the way it will soon be on our screen. So we, from our secondary schools, we know how to represent vectors, We could also represent it as a set letter of A. We could also represent vector as a single letter of A. Vector can also be represented as a single letter of A. So we could also do that for vector. Then modulus of a vector. The modulus or magnitude, when we say modulus, we mean the same thing as the magnitude of a vector. The modulus or magnitude of a vector is written in the form in the form A with double lines, A in between double lines. As soon as my screen comes up, I'll make it available for you to see. Now, for example, if we have a vector of A, then we can write the magnitude of A as one stroke A and another stroke. So we can do that perfectly. We can do that perfectly with the vector. We can do that perfectly. So we can do so many things, represent our vectors in so many ways. We can represent our vectors in so many ways. Please just be patient. My screen is about coming up so we can see what I'm actually talking about, because this thing requires you to see the screen, not me just talking without us seeing it. Just in few seconds, the screen will be up and we'll see what I'm trying to work on. So that is it. So before it comes up, let's continue. Then the equality of vectors. Equalities of vectors. We can also talk about the equality of vectors. The equality of vectors. Now, these are when two vectors are equal. If when two vectors are equal, if and only if they have the same magnitude and direction. We talk about the equality of vectors when two vectors are equal, and if and only if they have the same magnitude and direction. So that is when we say equality of vector. Now, in another we say A is equal to B, which implies that magnitude A is equal to magnitude B. The direction of A and B are the same. The direction of A and B are the same. In other words, they are having the same magnitude and direction. They are having the same magnitude and direction. So we'll say equality of vectors. That's when we say equality of vectors. Equality of vectors. So that is when we talk about the equalities of vectors, they are the same. They have the same magnitude. They have the same magnitude. They have the same magnitude. They have the same magnitude, the same direction, everything. They share everything together. They share everything together. They share everything together. So it's only then we can say, that we can talk about vector equalities. Only then we can talk about vector equalities. We can talk about vector equalities. So thank God my screen is back, so we'll be able to see it. And let me put it to where we will. Let me continue from the representation of vectors now, so everyone could see what I mean by this representation of vectors. Now, if you remember, I said if we want to take a line if we are joining a line a line of having 2 points from point A to point B. Now, if you see on my screen, this is the line A from point A to point B. That's the line from point A to point B. So that is the line from point A to point B, point A to point B line. So you could see that very well. So that is a way in which we can represent a vector. Is moving from A to B. So we can represent a vector in that way also. Then we can also write it as if you can see my mouse, we can also write it as AB or bar AB. So we can also represent vector in the same way, just the way you see it on my screen right now. We can also write it as this, and we could also represent it as letter A or this. So these are the ways we can represent vectors. These are the ways we can represent vectors. So now the other thing we do here, like I told you, is the modulus of vector, the modulus of vector, the modulus of vector, the modulus of vector. So when we talk about modulus of vector, I told you that the modulus is the same thing as everyone. Now we're talking about we're talking about angle between two vectors before the network issue. So if we consider two vectors, now see here we have two vectors. There are two possible angles between them, um, phi and theta. So you could see them phi and 180 minus phi. And the angle two vectors is uniquely defined. It's uniquely defined. You can see that from where I have here. It is the angle between their direction when the lines representing them diverge. So you see the line now diverging, the line between them diverging. So this is what I mean by diverge. Now let's look at Cartesian vector. Cartesian vector, with the little time we have before this, we log out today. Sorry for the interruption, network interruption. To describe the point in space where an object lies requires the use of coordinate system. The Cartesian vector is used to describe the point in space where an object lies requires the use of coordinate system. The coordinate system we use is the Cartesian coordinate system. The Cartesian coordinate system. That is the system we use. We first define a unit vector in each of the x, y, and z direction. In each of the x, y, and z direction. So if you look at it, we have this is our y-axis, this is our x-axis, and this is our z direction or y direction, x direction, and z direction. Now from here, you see that I is the unit vector along the x-axis. I is the unit vector along the x-axis, and j is the unit vector along the y-axis. Yk is the unit vector along the z-axis, or what you say z-axis. Now vectors into direction, into the for vectors into this space, we only have the x and y coordinates. For vectors into dimensions or two directions, we only have the x and y coordinates. That is vectors of the form a is equal to bracket open and close ax y ax a y ax a y. So written in vector form, or alternatively we can also write it as a is equals axi plus ayj, axi plus ayj. Now we are taking this from, don't forget that from the Cartesian I showed you, we have our x direction or x axis. I is the vector, the unit vector along the x axis. Yj is the unit vector along the y axis. So now we're not taking as a is equal to axi, in that is in the x direction, plus ayj in the y direction. In Cartesian form, it means we go ax unit along s axis. Now in a Cartesian form, this telling us that we go ax unit along, the network. We go AS unit along the S axis and AY unit up the X axis. AX unit along the S axis, AY unit along the Y axis. So have go at logic can do this. Now in drawing the following vector, draw the following vector r equals 2i plus 3j. How do we draw that? R is equals 2i plus 3j. So now we want to draw it in the Cartesian form or in a coordinate. So to do this, we must first move 2 units along the x-axis. Now normally I'll say, okay, choose a scale. We'll move 2 units. This is 1, 2, 3. And along the y-axis, we also move some, take a scale 1, 2, 3. Now what happens is this. Now since we are given r is equals to r, so this is 1, this is 2, we have our 2 here, and 3 units along the y-axis, that is 3, j. So we have our 3 here. We have our 3 here. So that's where we have that drawing. Now in 3D, for vectors, um, in 3D space, we have an extra base or basis vector along the z axis. So now we have to use this arrow is equal to matrix A all over y, sorry, A, Y, Z. So don't forget in the 2D, we only stopped at A and Y. Now is 3D, we are adding the basis, an extra basis, which is A, Z. We are adding an extra basis, which is A, Z. Or in the Cartesian form, we can write it as R is equal to AXI plus AYJ plus AZK, which means we go AX along the x-axis, AY along the AY units along the y-axis, and AK or AZ units along the z-axis, AZ unit along the z-axis. So you could see what will happen. Now let's draw a vector. Let's draw the vector with using this equation here. We have r is equal to 2i plus 3j plus 2k. Now what this is telling us is that r is equal to 2i, so it's along the x-axis. Distance 2, you take the distance 2 along the x-axis, and 3j, and you take your distance also along the y-axis. Now 2k is telling you take two distances along the z-axis. So we could have what we do there. So you see my 2 there, and you see my 3 there, and you see all you need to know about that. Now, algebra of vectors, we could move on the algebra of vectors. Addition, we'll talk about the algebra of vectors, addition, multiplication by scalar, magnitude of vectors. So these are what we'll look at. Let's look at vector additions. Vector additions. If we define two vectors A and B as ax ay and b as a equals ax ay and b equals bx by, the addition of two vectors is simply the addition of each component. Now we all can see the screen. Now my a plus b is equal to, you see it, bracket open and close, ax ay plus bx by, and this will give us, when you add ax plus bx, which we have here, and under we have ay plus by. So we have this here. The addition of two vectors is called the resultant of the two vectors. Please, let's note it. The addition of two vectors is called the resultant of two vectors. The resultant of two vectors. Subtraction is defined in a similar way. You can do the subtraction in a similar way. All you need to do is, instead of you putting the plus sign here, you just put the minus sign, just the way we have in here. You just put the minus sign. Then for multiplication by a scalar, let's look at this example. If we define a vector A as A equals bracket open and close ax ay and scalar, which I call alpha, we can find it as, okay, alpha a is equal to alpha into ax ay, which is equals alpha ax then alpha ay. Now what is this? Is because we are using the alpha to multiply each of the components in this bracket. We are using it to multiply, so that is what it will give us this as our final solution. Each component of vectors get multiplied by the constant, so we use that. Now what you notice is multiplication by a negative value of alpha, by a negative value of alpha or constant, whichever. So we could also do that. Now let's do some little calculation. Calculate the magnitude of the vector A equals bracket open ax ay and az, ax ay and az. We should first First, find the magnitude of the purple line here. Now, don't forget we are working on AX, AY, and AZ. So what we need to first do is find the magnitude of the purple line, and the magnitude of W by considering X, Z plane, by considering X and Z plane. By considering this, you find the magnitude of this. You find the magnitude of the purple line by considering the X and the Z plane. Now, the length of the purple line is found using simple Pythagoras. We are all used to Pythagoras formula from our secondary school. So let's see it here. You apply it here and say your magnitude W is equal to the square root of AX squared plus AZ squared. Now, AX squared plus AC squared. So when you impute the figures, we be able to get what we're looking at. So we are now able to find the magnitude of the vectors. By the time we impute the values, will come out here. This will now give us the magnitude of the purple line, which is the W. So we've not been able to find the magnitude of this purple line. To find the magnitude of vector A, now we use this simple formula here. Magnitude A is equal to the square root of AY squared plus the square root of AX squared plus AZ squared, all squared. So this will now give us AX squared plus AY squared plus AZ squared. Now we now have the magnitude of A as this. So we have our Y, and don't forget this was what we got as the magnitude of the purple line of W. Now let's quickly treat every situation question. Everybody pick up your pen and write. Find the unit vector in the direction of A equals 4, 1, and 2. Find the unit vector pointing in the direction of A equals 4, 1, and 2. So let's explain, talking about formulas. So now let's use a real real figure now. Now to find the magnitude of A, now like from, you don't forget I showed you the formula on how to find the magnitude of A. So we now have the square root of 4 squared plus 1 squared plus 2 squared. And when you do that, what will it give to you? I don't need to put the answer for you, so you should be able to give us the answer. So therefore, the unit of A is equal to A all over A magnitude. So we have this. We have this. So let's quickly look at the scalar products before we start winding up today. I think we still have we have less than 10 minutes to go. The scalar quantity or the scalar product, also known as the inner product or the dot product. If we take two vectors, A is equal to bracket open and close AX, AY, AZ, and B is equal to bracket open and close BY, BX, BY, and BZ, we have the following definition for dot matrix. Now A dot B is, you have your A, Y, AX, AY, AZ dot BY, BX, BY, BZ, and this will not give us, when you multiply them, we have our AS, BX, multiply AS, sorry, we multiply, we have AS, BS, which is our AS, BS, now AY, BY, which are AY, BY, and the third column, we have AZ, BZ, which is what we have here. So the dot product will be used extensively to calculate the angle between two vectors. So we use it extensively for that. So now let's calculate at the angle between two vectors. So this is an angle now to see from your side. So angle between two vectors A and B. To do this, we need to use the dot product. To calculate the angle between two vectors, we need to use the dot product, like what I told you before, which is also the scalar product or whatever you want to call it. So, or the inner product. So give it a name. We need to use it here. Now let's begin by considering the following triangle. That is this triangle. triangle A, this triangle that is having two vectors A and B. So if we apply the cosine rule, now we know this in our secondary school, the sine rule, the cosine rule, the tangent rule, and all of them. Here we are applying the cosine rule. Now we say that A squared is equal to B squared plus C squared minus 2BC cos theta or cos phi. Now, putting this in our triangle, putting this formula now in our triangle, we have magnitude B minus A, magnitude B minus A squared is equal to B squared plus A squared, B squared plus A squared, magnitude B squared plus magnitude A squared minus 2 magnitude B magnitude A cos phi or theta. Now that is exactly, we just brought this into our triangle, just brought this into our triangle. So when we go further, we have B squared, magnitude B squared plus magnitude A squared minus 2AB, 2AB or 2 dot AB. This will now give us magnitude B squared plus magnitude A squared minus 2 magnitude B magnitude A cos phi. So therefore, we now have A dot B is equal to magnitude A magnitude B cos phi. Therefore, we now have our cos phi as A dot B all over magnitude A and magnitude B. So we were able to get this from our solvings here. Now, I believe every one of us knew how we got this from this. If you don't know that, just try, look in depth. Some has to go for some to remain. So some have to be cancelled for some to remain. So what do we do? Now, if you look in depth, this one has to go, this one has to go, this one had to go, this one had to go. So, and we now have this and this, we have this and this. Now let's also try this. If we find two vectors, if we find two vectors A and B, I want everybody to try this. Find two vectors A and B as A is equal to bracket open AX AY and B is equal to bracket open BX BY. Then the dot product or the scalar product or the inner product is defined by the following expression. A dot B is equal to magnitude A magnitude B cos phi. Now where phi is the angle between the two vectors. Now you can change this to theta, whatever you want, the angle between two vectors. Now the angle between two vectors is always defined as the angle between the points where they converge, So A dot B now will now give us AX BX plus AY BY, then and magnitude A and magnitude B are the magnitude of the vector A and B. So I will take this. Do we still have enough time? Let's take it as an assignment. Okay, we take it as an assignment. We have less than 5 minutes. Let's take this as an assignment. This question, calculate the angle between the vectors A is equal to bracket open 3, 4, 1, and B equals bracket open minus 2, 1, 3. So let's do that. Let's do that. If you can screenshot it, please screenshot it. It's an assignment, and please do it and submit it to safetybliss@yahoo.com. I spell for you safety, SAFETYBLISS@yahoo.com. Please take the question again. Calculate, you can see it on my screen, so I'm just reading it for emphasis sake. Calculate the angles between the vectors A equals to bracket A3, bracket open and close 3, 4, 1, and B equals bracket open and close minus 2, 1, and 3. Please, let's try that. Properties of dot products. Properties of dot product. Let's quickly rush over this before our time ends. We have two vectors A and B which are perpendicular to each other. Now A and B are perpendicular to each other. The angle between them is angle 90. You get that from our secondary school, that the angle between them, the vertical and the horizontal line, is angle 90, and we see that A dot B is equal to 0. If two vectors are perpendicular, their dot product is 0. Please note that when two vectors are perpendicular, their dot product is 0. So I want us to take this question. Please, let's take this question also to end this class today, and take this question on the screen. Define what is meant by a vector and differentiate between a vector and a scalar quantity. That is assignment. And this is second assignment at question 2. Define what is meant by a vector and differentiate between a vector and a scalar quantity. 3. Algebraically manipulate a vector. Algebraically manipulate a vector. 4. Calculate the angle between two vectors using the scalar product. Calculate the angle between two vectors using the scalar product. So define what is meant by a vector and differentiate between a vector and a scalar quantity. Algebraically manipulate a vector, and 4 rather, calculate the angle between the two vectors. So please, this assignment must be submitted not later than tomorrow, 23:59 p.m., not later than tomorrow. This assignment should get to us. Our next class will be meeting on Thursday again. So till we meet on Thursday, remain safe and stay calm. God bless you and have a lovely night rest. Bye-bye.